Ever stop and think about the chair you're sitting on? Why it doesn't just collapse? Or how the building you're in manages to stay perfectly upright? It seems obvious, right? But it's actually all thanks to this powerful, invisible science. Today, we're diving into the world of statics. This is the fundamental science that is literally keeping our entire world from falling apart. Let's see how it works.
I mean, just look at a structure like this bridge. It is massive. It's carrying an unbelievable amount of weight day in and day out, and yet it stays perfectly still. So how does it do that? How do engineers actually design things specifically so they don't move? Well, that's the big question we're going to answer. And the answer is a field of study called engineering statics. You can think of it as the first step into the much, much bigger world of engineering mechanics. And it's all about understanding objects that are in equilibrium, which is really just a fancy way of saying they are holding perfectly still. So what is statics exactly? To put it really simply, it's the study of things that don't move, things that are static. And this is the foundational physics for pretty much everything that isn't supposed to move, from the tiniest little screw inside your phone to a huge, towering skyscraper. You see, statics is right at the heart of what some people call the engineering mechanics trilogy. You absolutely have to master the science of no movement before you can even think about tackling dynamics, which is the study of things that are moving, or the mechanics of solids, which is all about how things bend and stretch under pressure. It's the essential starting point, the foundation for everything else. Okay, so how does it all work? How can an engineer guarantee that a bridge or a building is actually going to stay put? Well, it all boils down to one simple but incredibly powerful principle. I like to call it the engineer's golden rule. And here it is. This little equation, this is the whole secret. In the language of math, it says sigma F equals 0. Now, it might look almost ridiculously simple, but don't let that fool you. This one core idea, borrowed from Newton's laws, is the foundation for the entirety of statics. And what this means is, well, it's kind of revolutionary. For any object to be static, to be perfectly still, the sum of all the forces acting on it has to be 0. Every single push, every pull, every twist, all the weight, everything has to be perfectly balanced by an equal and opposite force. They have to completely cancel each other out, no exceptions. Now that's a great theory, right? But how do engineers actually use it? I mean, you can't just look at a bridge and see all the hidden forces pushing and pulling on it. To use that golden rule, you first have to make those invisible forces visible. And to do that, they've got some pretty essential tools. But before we get to the main tool, let's clear something up that trips a lot of people up. It's something that is absolutely crucial for an engineer to get right. What's the difference between a pound of mass and a pound of force? The authors of the textbook we're looking at felt so strongly about this, they actually wrote a song about it to make the point crystal clear. When an engineer says pounds, they mean pounds of force. In statics, that's a rule you have to live by. Let's break it down. Mass is just the amount of stuff in an object. You'd measure that in kilograms. Weight, on the other hand, is the force of gravity pulling on all that stuff. That's what we measure in newtons or pounds force. They are not the same thing, and you know what? Confusing them can lead to some pretty catastrophic failures. Okay, with that cleared up, let's get back to making forces visible. The single most important tool in an engineer's toolbox for solving statics problems is something called a free body diagram, or an FBD. This is how they turn a really complex, real-world object into a simple problem they can actually solve with math. And making one is basically a 3-step process. First, you isolate the one thing you care about. It could be a single beam, a cable, or even the whole bridge. Second, you draw arrows representing all the external forces acting on it. So gravity pulling down, the supports pushing up, maybe the wind pushing sideways. And third, you apply that golden rule. You set the sum of all those forces to 0. And then you can solve for anything you don't know. So now let's see how all this theory actually builds the world around us. Because understanding these diagrams and equations isn't just some boring academic exercise. It's literally what allows us to build our modern world safely and reliably. This is where it gets really cool. Statics is the absolute bedrock of all the major engineering fields. For civil engineers, it's what keeps those bridges, buildings, and dams standing strong. For mechanical engineers, it's essential for creating everything from a sturdy car frame to a reliable robot on a factory floor. And for aerospace engineers, it's what guarantees an aircraft structure can actually withstand the immense forces of flight without falling apart.
The scale of these principles is just mind-blowing. The exact same rule, sigma F equals 0, is used to guarantee the safety of a bridge carrying thousands of cars every single day, and an orbiting spacecraft that has to endure the totally hostile vacuum of space. It really is the universal language of stability.
All right, let's bring this all home. We've looked at the core rule, the tools, the incredible applications, but why does this science of stillness, the science of perfect balance, really matter to you in your everyday life?
Here's the bottom line. Statics is the silent partner to all of our human ambition. It's this quiet, fundamental science that's always working behind the scenes, making sure every single structure we rely on, every single one, is safe, stable, and secure. We never even notice it when it's working, but believe me, we would be completely lost without it.
So I'll leave you with this thought. Just for a second, take a look around you. The floor beneath your feet, the roof over your head, the chair you're sitting in. Every single one of those is a tiny, silent battlefield of perfectly balanced forces. So the question is, what invisible forces are holding your world together right now?